on the other part. All right, so look at your square roots. Can you break those down?
No.
No. Can you combine these?
No.
No, you've already done number 2. That's the answer. I doubt you'll get that lucky on a quiz or a test, but it's important to know that. You would split, oops-a-daisy, split, oops, working faster than writing, and then simplify.
Okay.
All right, so I'm going to distribute, right? I'm going to distribute the first, which is 4 times 3, that's 12. Square root 5 times square root 5 is 5. Then I go to the outer 2. 4 times 2 is 8 times root 5. Then I go to the inner 2. Negative 1 times 3, negative 3 times root 5. And then I go to the last, negative 1 times positive 2, negative 2. So then 12 times 5 becomes 60. 8 root 5 minus 3 root 5 becomes 5 root 5. Minus 2, which these two can be combined, 58 plus 5 root 5.
Okay, thank you.
Kind of mess up like the whole problem, like my answer. So
You're right. You're right. So remember, you want to for me, I like to split them up. I make it square root 32 and then square root of b to the 4th. So 32, 2, 16, right? Which is 4 and 4. I could just bring out a 4, or I could break down 2, 2, 2, 2 again and bring out 2. But I could just do the 4 root 2. That's the 32 part, right? And there's only 4 b's. So if you really wanted to write it out, you could, so that if you're questioning yourself, each pair of b's is going to bring out a b, right? Which means it's 4 times b, which is b squared, times root 2. But the other way to do it, because the more variables, the higher the exponent, the harder that's going to be, you take the index, which is a 2, and you divide it into the exponent, and that's the exponent on the outside. So if I did 2 into 4, it'd be b squared, and then that goes to the outside of the square root.
That's the way I was taught to do it, because we did this a little bit.
Perfect.
In algebra, so.
Good.
Okay.
Yeah, that's right. No problem. All right, so 11, right? 75 I'm going to break down. I'm going to split them up. 75, and then the square root of r to the 3rd. 75 is 3 and 25, which is 5 and 5. So I bring the 5 to the outside. The 3 stays underneath. And then if we do it the division way, 2 goes into 3 one whole time. So that's how many r's are going to be multiplied on the outside times the 5. So I get 5r. But there's 1 left over that's going to stay underneath the root with the 3. If you want to spread it out, then you could do r times r times r. 2 of them go to the outside with the 5, and the one that doesn't have a pair stays underneath with the 3. So your answer should have looked like this: 5r times the square root of 3r.
Also, how do you do number 2?
2. Oh, all right. So for me, I would start by simplifying to make it smaller numbers, right? Doesn't mean you have to do it this way, but 2 goes into 14 7 times, so that makes it a little bit easier. And then 5 goes into 320. What is that? 64 times. So you end up with 7 square root 64, and then square root 64 becomes 8. And there was nothing left in the bottom because the 2 goes into itself once and square root 5 once. So it's just 56. All right, so we are going to pick up where we left off yesterday. We talked about simplifying radicals and square roots, right? We said that if we're going to simplify it, 2 of that number has to be there in order to come to the outside. We said that we can multiply square roots. We would multiply what's underneath the root together. If there was a number on the outside, we multiply the numbers on the outside and then the numbers underneath the roots. And we said we can simplify when dividing. We can divide this 5 into the 10, and I get square root 2 over square root 1, which is just square root 2. So we talked about that yesterday. We worked through these examples and these examples yesterday, so we are here. We're on examples, continue number 9. Example number 9 is where we left off, okay? So if I look at number 9, It says square root 5 times square root 5 times square root 9, right? So because they're all underneath a root, I can actually multiply them all out together. It could be 5 times 9. But before I do the math on that, before I do 5 times 5 is 25, 25 times 9, right? I don't want to work through all of that if the whole goal is to break it back down again. So what you want to do is, if it's already broken down, like the 5 and the 5, leave it that way. And then the 9 we can actually break into 3 and 3. Now, because it's a square root, we need 2 of those. 2 5s go to the outside of the square root. 2 3s go to the outside of the square root. I multiply that together, and I get just square root 5. Or sorry, just 15. So if I had multiplied them all out, I would have gotten square root 225, which is 15. But obviously, you're dealing with bigger numbers, okay? It's easier to keep them broken down. So number 10 is square root 11 times square root 44. So I can write them all underneath 1. I can also keep them with it as. So here I've got my 11. 44 would be 4 and 11. 4 is 2 and 2. Now I've got 2 11s, so an 11 comes to the outside. And I've got 2 2s, so a 2 goes to the outside. And this is 22. Questions on that one? All right, you do 11. All right, so the 11 doesn't break down, but the 33 is 3 and 11. That means there's 2 11s, so 11 goes to the outside. This time, this 3 doesn't have a pair, so it stays underneath all alone because it doesn't have a partner, okay? Stays isolated all by itself, just like all of us are, underneath the square root. And I'd get 11 square root 3. Everybody still good? Yeah? Okay. Now we get into the dividing. So remember, if there are a numerator and a denominator both underneath the square root, that we can simplify these, right? So 7 goes into 35 5 times, and I can rewrite this as 6 over the square root of 5. Now here's the catch with what's called rationalizing. You cannot leave a square root in the denominator, okay? We're going to come back to this because we're going to break down in a little bit what rationalizing is. We will come back, I promise we'll come back to this example, but for right now we're going to leave it this way. Now go to 13. 39 does not go into 48. Is there a number that goes into both 39 and 48? I'll give you a hint. There is.
3.
Good. It's 3. So 3 can go into this. It'd be 16 times. 3 can go into this. It's 13 times. So if I rewrite that, that's 5 square root 16 over square root 13. Can I simplify that further? What's the square root of 16? 4. So this becomes 5 times 4 over square root 13. And I get 20 over square root 13. And again, we're going to come back to what happens when I have a square root in the denominator because I have to do something with that. But for right now, we're going to leave it like it is. Questions on any of those? All right, now we're multiplying. So we're going to use our distributive powers, okay? So this root 5 gets multiplied into both of these terms. Square root 5 times square root 5 is what?
5.
5. Square root 5 times minus 2 would be negative 2 root 5. One's got a root 5, one doesn't. I cannot combine them, so they're going to stay that way. Now I go to 15. I've got 3 different terms here being multiplied together. I'm going to go group all the coefficients. So 3 times 2, root negative 2, which is negative 6, times 3, negative 18. That's the numerator. Then let's group together all the numbers underneath the square roots. So it's 2, 8, 27. 2 cannot break down any further, but 8 can be 2 and 4, which is 2 and 2. 27 is 3 and 9, which is 3 and 3. Now every pair is going to go to the outside. So I've got one pair of 2's here. I'm going to bring it to the outside. Another pair of 2's here. I'm going to bring it to the outside. A pair of 3's, bring it to the outside. The only dead end branch left is the single 3. So I'm going to multiply all this together. This would be 4 times 3. That's 12. Negative 18 times 12. 216. So negative 216 square root 3 is my most simplified answer. So we group together all the numbers on the outside, all the numbers on the inside. We break down all the numbers on the inside till they're prime, and then see if there's any repeated pairs. Bring all those repeated pairs to the outside. Questions on that one? All right, now we've got back to the division, but there's a number on the front, right? We still just focus on the roots. Does 6 go into 90?
15.
Good. So this is 1. This is 15. 15 times the square root of 1 is just 15 over the square root of 15. 15 is just 3 and 5. It doesn't get broken down any further. So for right now, we're going to leave it the way that it is.
Wait, are we going to learn that today or another time?
You're going to learn that today. I think it's in 2 slides.
Okay.
Yeah. Yeah, 2 slides.
Why can't we have a square root in the bottom?
It makes it irrational, which, again, I'll talk to you about. It's literally in 2 slides. I should have reversed it, but this stuff came first. All right, last one on this slide is 17, and now we're subtracting. So multiplying we can do, right? Multiply the outsides and the insides, but this is subtracting. You can only add or subtract if the root is exactly the same, just like if the variable is the same. They both have a square root 3, which means we can actually combine these. The root 3 stays as root 3, just like an x would stay as an x. But the coefficients on the front, you're going to add or subtract. This time subtract. So 8 minus 6 is 2.
If they had different radicals under the square root, would it just stay the way it is?
Yep. So if it's something like this, 8 root 2 minus 6 root 3, those are completely different roots. I can't combine them. You always want to check to see if they can be simplified first, because they might be able to be simplified and then combined. But like this, you can't combine them. They would stay separate.
Okay, thank you.
You're welcome. Any other questions before we move to the next set of examples? All right, so speaking of simplifying and then combining, look at number 18. Negative 2 root 24 minus 3 root 6. So as they are, I cannot simplify them. I cannot combine these. But 24 breaks down into 2 and 12, 2 and 6, 2 and 3. 2 2's comes to the outside, gets multiplied by the negative 2 that's there, making that negative 4. The 2 and the 3 are left underneath. Multiply that out, and I get root 6. Minus, bring this down, 3 root 6. Now they both have the same root, which means they can be combined into one term. 4, negative 4 minus 3 becomes negative 7, and the root 6 stays as it is. All right, 19. See if you can break that apart. So you try that. See if you can simplify it, and then see if once it's simplified, if you can combine it.
So with the 45, it can be broken down into 9 and 5, and 9 can be broken down into 3 and 3. So you take out the 3's and you multiply those by the coefficient 3, which gives you 9 radical 5. And then for the 7 and 36, 36 is 6 times 6. So you can take those out and multiply them by 7, which gives you 42. So you get 9 radical 5 plus 42.
Perfect. And you can't combine them, right? Because one's got the square root 5 and one doesn't. Good job. Questions on that one? So don't assume you'll always be able to simplify and condense. You might be able to simplify and maybe not condense. All right, 21, we're dealing with a multiplication, right? We're multiplying binomials here. So this is foiling, okay? We're going to multiply the first terms in each. 4 times 4 would be 16. We're going to multiply 4 times the last one, so the outer. 4 times negative root 11 would be minus 4 root 11. Inside is root 11 times 4. This time it's positive 4 root 11. And last, root 11 times negative root 11 becomes negative 11, because square root 11 times square root 11 is just 11. Now we combine our like terms. I've got two constants, 16 and negative 11, which becomes 5. Positive and negative 4 root 11s cancel out, and my answer is just 5. Now there is a shortcut there, which we'll talk about special products in the next section, but there is a shortcut. All right, 22. Now I've got something squared. So if it's squared, it means duplicate it. It does not mean distribute the squared into it. And there are grown adults that still do that. That is wrong. You cannot distribute a squared. You got to expand and then FOIL. So first, this time first has two terms. 3 times 3, which is 9. Root 7 times root 7, which is 7. Outer, 3 root 7 times negative root 3 is negative 3 root 7 times root 3, which is root 21. Inner, negative root 3 times 3 root 7 is negative 3 root 21. And last, negative root 3 times negative root 3 is a positive 3. This becomes 63, and then I have two constants, 63 and 3, so that's 66. Now I've got two root 27s, and they both have a negative 3. Minus 3 is negative 6 root 21. 21 can't be broken down past 3 and 7, so there's no repeated ones, right? So that stays as my answer. Questions on those? Okay, so now, oh, did I not? I didn't do 20, just kidding. Let's do this one real fast before we move on. 32 would be 4 and 8, which is 2 and 2, 2 and 4, 2 and 2. That's one pair of 2s, 2 pairs of 2s, and a 2 that's going to be left by itself. 3 times 2 is 6, times 2 is 12, root 2. 63 is 7 and 9, which is 3 and 3. The 3's go to the outside, get multiplied by that minus 4, and I get minus 12. 7's left underneath. Different roots. Even though the coefficient's the same, the roots are different, so I have to leave it the way that it is. All right, now we did all those. Questions on any of those before we move on? All right, so here's the dividing of the radicals, which we did this somewhat, but it says square roots must be eliminated from the denominator, okay? Otherwise, they're called irrational. And in that case, the thing that we are going to do is called rationalizing the denominator. So we are eliminating the square roots on the bottom by doing what we call rationalizing the denominator, okay? And that process is multiplying both the numerator and the denominator by whatever square root's in the bottom. We're going to simplify the numerator, and when we multiply the denominator, which is a square root by itself, it gets rid of the square root. If there's an expression in the bottom, if it's not just a single term, if it's something plus something or something minus a root, then we multiply by the opposite expression. So I'm going to work through each of these. 5 root 2 has root 2 in the bottom and it can't stay there. So I multiply both the top and the bottom by root 2. This is called rationalizing the expression. The reason we can do this is because root 2 over root 2 is really just 1. And you can multiply anything by 1 and it doesn't change the value. So we're not changing the value, we're changing how it's written. Then I would multiply straight across. So 5 times root 2 is 5 root 2. And root 2 times root 2 is just 2. Got rid of the square root in the denominator. So square root in the numerator is totally fine. You can't have it in the denominator. Second one has a plus in between. This is an expression, so I can't multiply this by root 3. I mean, you can, but it's not going to get rid of the square root. So we multiply it by the opposite of this expression, which means keep the numbers the same but change the sign in between them. So I multiply both the numerator and the denominator by 2 minus root 3. So this would be like having this in parentheses. I'm going to distribute the 2 into both of these, and I get 4 minus 2 root 3 over, now I multiply out the bottom. 2 times 2 is 4. 2 times minus root 3 is negative 2 root 3. Root 3 times positive 2 root 3. Root 3 times negative root 3, negative 3. These cancel, and I get 4 minus 3, which is 1. You won't always eliminate the number in the bottom, so really this answer is just 4 minus 2 root 3. I can have a denominator, but that process has to eliminate the radical from it. So sometimes you'll have a number in the bottom, that's fine. It just can't have the radical. Questions so far?
What's the problem if you have it, what's the problem with it being irrational?
So it's just an irrational number which doesn't end and doesn't repeat, and you can't keep that in the bottom. So non-perfect squares are called irrational numbers that can't be left in the bottom. Yeah.
Okay.
So in example 16, we had root 15 over root 15. So in that case, I would multiply both the top and the bottom by the square root of 15. And I'd get 15 root 15 over 15. And that simplifies to just square root 15. So sometimes you can simplify once you get rid of the denominator. Sometimes it stays, sometimes you can actually simplify. All right, let's work out some examples. So what do I do with 23? What do I multiply both the top and the bottom by?
Square root 3.
Good. So root 3 over root 3. 7 times root 2 times root 3 becomes 7 root 6. And root 3 times root 3 is just 3. Now 3 can go into the 6, but one's a root and one's not, so I can't simplify it. 3 can't go into 7, so I'm going to leave it the way that it is. So if your constants can be simplified, you can. If you had 2 radicals that can be simplified, you can, but you can't put a radical into a constant into a radical. You can't simplify it that way. All right, 24. Again, the root in the top is fine. The root in the bottom is the problem. So I'm going to multiply both the top and the bottom by the square root of 3. So this is still the distributive property. It's just that the order is reverse. Okay, I'm going to distribute the 4 and the 3, or the root 3 to the 4 and the root 3 to the root 2. So this becomes 4 root 3 plus root 2 times root 3, which is root 6, over root 3 times root 3, which is 3. Again, I can't cancel something outside a radical with something inside the radical, like the 3 and the 6, so my answer stays exactly like that.
With the 3, with the radical 3 and the radical 6, because in problems before, we when we did like the 11 and the 33, would it only work to take out, like, for example, with radical 11 and radical 33, to take out the 11 from both of them, it would only work if you're multiplying them?
Exactly.
Okay.
Yep. So when you're adding, they have to be the same radical. So you can't reduce them. But just think about the same if you had x squared plus x to the third, right? We can't combine those. They're two completely different things. But x squared times x to the third, we can multiply those, right? The same rule applies with the square roots. If they are the same square root, we can add them. If they are not, we cannot. But if they are different square roots, we can multiply them.
And when we're dividing, do they have to be the same also?
In order to eliminate them or to rationalize. So like if I have square root 6 over square root 3, that I can reduce.
So if when multiplying and dividing, to rationalize, they don't have to be the same as long as they have a common...
As long as they're both square roots. So you can't do it with a square root and a cube root. But you can do it with two square roots. Yep. But adding and subtracting, they have to be the same root. Exactly the same. Not the constant on the front, but what's underneath it has to be the same.
How is this problem different from the one that we did before? The one that we did for example?
Which example? Why is
The
this?
radical on the denominator.
Hang on, I'm
Two
not.
above.
How is it different from that one?
Rationalizing the denominator.
Oh my
How is it
word.
different?
Sorry, it's not letting me. Hang on. It's not letting me zoom out. Oh, you pain in the butt. I don't know what is happening right now with Explain Everything. There we go. Okay. With, like, you mean 23? Which I just lost, but.
No, 24, and then the one from the page before where we had the...
So the page before, good question. The page before, the sum was in the bottom.
Oh, yeah.
Now the sum's in the top. So if you only have a single term in the bottom, you only have to multiply by that single term, no matter what's in the top. But if there's a sum in the bottom, like 25, this is like the one that was on the example before.
Yeah.
That you have to multiply by the opposite. So it depends on what's in the bottom. Is the bottom a single term? A single radical? You just multiply by that radical. If it's not, if it's a sum or a difference, then you have to multiply by the opposite.
Okay.
So which is this one? You're welcome. So 1 times this is just that. That's 3 minus root 2. The denominator, I have to do 3 times 3, which is 9. 3 times negative root 2, negative 3 root 2. 3 times root 2, positive 3 root 2. And root 2 times negative root 2, negative 2. The middle should always cancel out. The whole point here is to eliminate the radical. And then I get 9 minus 2, which is 7. So I have 3 minus root 2 over 7. All right, last one, most fun, right? Because you've got a expression in the top and the bottom. I look at the bottom, I say the bottom's a problem because of the root. I multiply it times 1 plus root 2. But now I have to do the top and the bottom by 1 plus root 2, which means I'm going to have to FOIL the top and the bottom. So let's FOIL the top. 3 times 1 is 3. 3 times root 2 is 3 root 2. Root 2 times 1 is root 2. Root 2 times root 2 is 2. Combine my like terms here, and I have 5 because of 3 plus 2, plus 3 root 2 plus 1 root 2, which is 4 root 2. That's my numerator. Denominator, 1 times 1 is 1. 1 times root 2 is positive root 2. Negative root 2 times 1, negative root 2. Negative root 2 times positive root 2, negative 2. Like it's supposed to, Square roots cancel. I get 1 minus 2, which is negative 1, and that's the denominator. Now what happens when you divide by a negative 1?
The whole thing becomes negative.
It just changes those signs, right? So this becomes negative 5 minus 4 root 2. That's the most simplified form. So if it's over 1, you want to get rid of the 1. If it's over negative 1, you change the signs on the top and also get rid of the 1. Questions on those?
Can you go back to 25?
Sure.
Okay, thanks.
You're welcome.